and thank you for the introduction. But if I can, a little bit more about me. So I'm Aruna Chandrasekar. I recently finished my PhD in chemical engineering from University College Dublin. So basically, over there, I looked at the role of natural gas and hydrogen in a future interconnected energy system. Prior to my PhD degree, I pursued my master's degree at TU Delft in the Netherlands, where I looked at maximizing syngas production from plasma gasification unit, which was to be used in a solid oxide fuel cells. This area is not new to me. I've been working on it for quite some time. So actually that concept was used in the Bill and Melinda Gates. It was used in a project funded by Bill and Melinda Gates Foundation to reinvent the toilet, to build a self-sustained toilet. That was very interesting. Prior to that, I did my bachelor's in chemical engineering from BMS College of Engineering in Bangalore in India in chemical engineering. So basically, I'm a chemical engineer. Today I'll talk a little bit about green hydrogen projects around the world, my role in EPRI, that is the Low Carbon Resource Initiative, a little bit about how EPRI is approaching the challenges that we are facing or that we will face as we transition towards a low carbon future. So this map, so I got this map actually from, I think, Pillsbury Law Law Institute, and they actually made this map called the hydrogen map. I just really like this. So basically shows the total number of hydrogen projects, which includes blue, green, and grey hydrogen production around the world. So we see that as of 2021, and just bring up a laser pointer because that helps. So we see that as of 2021, the number of green hydrogen projects around the world, particularly in Europe, has boomed. And another report by McKinsey and Company, and this report was in 2021, it shows that over 200 projects have been announced globally, with over 126 projects in Europe alone. So Europe is really looking at hydrogen, particularly green hydrogen, for the future. And one of the primary motivations behind green hydrogen, because by definition, green hydrogen is hydrogen production from renewable electricity, which is why green hydrogen, is to basically make more efficient use of the renewable electricity production. So just because this topic is kind of focusing on offshore wind, and also offshore wind is becoming increasingly researched in particularly Northern Europe and also in the East Coast, particularly, or even the Pacific coast of the United States. So we have offshore wind production is a source of, it is a source of renewable electricity, but particularly in Northern Europe. And even though US offshore wind is basically lagging a little bit with the advent of floating offshore, where basically the wind farms can be situated in kind of deep inside the Pacific, where we can make much more use of the potential wind energy from there. Hence, the idea is to make wind energy a lot more reliable so that we can potentially operate them at high capacity factors. But I will touch upon the reliability of renewable electricity production a little bit later as well. So some of the challenges with offshore wind development, which also kind of transcends into other kinds of renewable electricity, is that we're not able to exploit the full potential of renewable electricity in case of offshore wind, because it has to withstand harsh marine environments, but also construction and maintenance at sea requires specialized skills. And with a lot of renewable electricity development, we need specialized skills. But also with offshore wind, it's more expensive compared to current mature technologies. Hence, we want to lower the cost of electricity production as well. And these are at a high level. At EPRI, however, what we are focusing on is looking at the decarbonization pathways that are lead to more efficient electrification. So we can, in this case, for example, in order to make more efficient utilization of offshore wind, what we can do is operate them at higher capacity factors, but also make full use of the renewable electricity by by being able to store potentially curtailed renewable electricity. So to tackle this challenge, so basically EPRI looks at a system-wide approach to accelerate the economy-wide decarbonization. And so in the past, there has been a focus on increasing the energy efficiency and moving towards cleaner electricity. But in addition to that, in order to kind of speeden up the process of moving towards a low carbon system, EPRI also focuses, Electrical Power Research Institution is also focusing on efficient electrification and moving towards low carbon resources such as hydrogen and ammonia. As a result of this, we have started an initiative called the Low Carbon Resources Initiative. So Low Carbon Resources Initiative is a 5-year initiative that focuses on advancing low carbon fuels across the energy system. So the 4 focus areas are low carbon fuels production pathways, storage and delivery of low carbon fuels, end-use applications of low carbon fuels, and a cross-cutting value chain approach to analyzing the impact of using low carbon fuels in an integrated energy systems analysis. So this initiative is both by Electrical Power Research Institution and Gas Technology Institute, which is gas research institution in the US based in Chicago. So we're collaborating with them in this initiative. And just to show, this slide is basically just to show kind of, we've received a lot of industry interest. So this initiative is jointly led by GTI and has over 50 industry sponsors, not just electrical and gas utilities. I mean, it mainly comprises of electricity and gas utilities, but also OEMs and EPCs. And we constantly have members interested in the Low Carbon Resource Initiative. We have many supplemental projects as well to support projects relating to this. So just to give a very brief high-level overview on this, and I'll go into detail about the electrolytic processes. So in order to facilitate basically the research, it looks at an entire energy systems approach, and it's divided mainly into 8 technical subcommittees. So we have electrolytic process, which falls under the production pathways. And then we have hydrocarbon-based process and renewable fuels. Hydrocarbon-based process looks at steam, methane, reformation, carbon capture and storage and utilization, direct air capture. Then we have renewable fuels, which looks at biogas and biomass production. And then the delivery and end use side, we have, of course, storage and delivery of low carbon fuels, power generation, that is low carbon fuel power generation, and also the end use sector, which looks at transportation, that is using these low carbon fuels in the transportation, industrial and building sector. And one of the novelty of the Low Carbon Resource Initiative is looking at the cross-cutting approach, and that is looking at the safety environmental aspects throughout each the entire energy system, looking at the safety environmental aspects that need to be considered, and also the integrated energy systems analysis, which basically looks at a model that uses the results, uses inputs from all of these other 6 technical subcommittees, and this model analyzes all of these inputs and looks at an economy-wide decarbonization pathways and impact assessment. So a little bit about the electrolytic process, because that is my specialty, and also looking at how in EPRI, how we are planning on tackling particularly the operational challenges that we encounter when we're moving towards a low carbon energy system. So so basically with that in mind, so basically the vision of the electrolytic processes was to research areas basically that look at grid and energy integration, looking at the performance and reliability impacts, looking at electrolyzer technology development and the electrolysis systems, combining that with, of course, as I mentioned, the environment, health and safety aspects. We collaborate with the manufacturing and materials, because constantly new and new novel electrolyzer technologies are being developed. and also look at fuel production and integration, particularly with between the electricity and gas grids. We're using a primarily modeling approach in that ammonia synthesis, where GTI has a specialization in ammonia, so we are collaborating with them on that as well. So some of the focus areas of the electrolysis TSC is looking at the balance of plant components, understanding system degradation, which is actually a major challenge, particularly if we look at in future, we will have a challenge of system degradation, and not just stack degradation, but an entire system-wide degradation. Modeling the flexible operation of electrolyzers, which actually I am primarily focusing on. Looking at the techno-economic analysis, we've already developed an online tool for the industry members to basically be able to calculate hydrogen production based on technology, capacity factors, and fixed operation maintenance costs, which could vary from place to place. And we also have a collaboration with the National Renewable Energy Laboratory in the US, which looks at, we are able to leverage their electrolyzer technology and look at production and performance of the electrolyzer in base load and flexible operation. With that in mind, so just primarily, so we have, this is in the electrolyzer field is common knowledge that we have primarily 4 electrolyzer technologies consisting of the alkaline electrolyzers, which are one of the most mature electrolyzer technologies. Then we have the PEM electrolyzer, which basically make use of a solid membrane. We have the SOEC, which is solid oxide electrolytic cell, which is a high temperature electrolyzer. Also making use of a solid membrane. And then we have an anion exchange membrane, which is basically uses the concept is that of an alkaline electrolysis, but makes use of a solid polymer electrolytic membrane. So it's somewhere between an alkaline electrolyzer and PEM electrolyzer. So in the electrolytic process group at EPRI, when we are looking at these 5 research topics, we include analysis in all of these 4 technologies, and as a result of that, actually one of the main kind of projects that has come out of it is the tech scouting projects, basically where we could have novel electrolyzer technologies that probably are in research stage now, but could reach maturity in a few years. And so we are also consider novel technologies while looking at balance of plant component, let's say for an alkaline electrolyzer. We also look at novel electrolyzer technologies that could transcend this curve and reach technology maturity, and it could aid in our mission for a low carbon future. So, as I promised, so the project that I focus on is understanding how we can maximize hydrogen production and lower systems cost during the flexible operation of an electrolyzer. So as I mentioned, so whenever we look at renewable electricity generation, whether it's from offshore wind, as I mentioned before, or whether it's from solar generation, and the reason I mentioned solar generation is because we have this very nice curve that's been generated by the California independent systems operator. So whether we have offshore wind, whether we have solar, we have the risk of curtailment due to overgeneration of renewable electricity. That is to say, so when we have periods of low system demand, the sun shines the brightest during the middle of the day, but we have low system demand during that time, because of which, with higher penetrations of renewable with solar electricity, we could have the risk of curtailment, that is overgeneration. So this is the California Independent System Operator. They generated this curve. Sorry. So they generated this curve, but we see a similar curves being, we observe similar curves in, let's say, Germany. So we have the German duck curves. So the system demand curve could look a little different, but the concept is still the same. So We see actually a similar kind of curve with wind as well. It's called, I think, the Gator curve. So basically, with increased system demand, with increased wind penetration, we have increased risk of curtailment. And the problem with increased curtailment is investors won't get maximum returns on their investment in renewable electricity, drives up prices of renewable electricity generation, and risk of not having energy when we need it. That is to say, when I switch on my lights, my light may not switch on because my system is entirely depending on renewables. So what I study, so what we would want to do is, so when we have particularly multi-renewable electricity generators, so we need to look at, so the role of flexibility, I would put it this way, so the role of flexibility is basically to provide energy, when or demand response when the renewables are not able to meet, and particularly if we are moving towards 100% or even a high renewable electricity system, we need to look at storage options. And in this case, I'm showing a system demand of a typical US day, but of course it's just an example. So we have this is an example. So we have, this is the electricity demand. If we have in the side, we see this is a typical wind, where wind is variable, not just on a daily, but also a seasonal basis. So we have solar production, which peaks during the day, and there is some overproduction here. And we have nuclear. In this case, we just use nuclear as an example. We have nuclear, which typically operates as a base load. And when we combine these three, nuclear need not be renewable, but these three electricity generation units and storage could basically be used. In this case, it's a diurnal storage, but it could also transcend to seasonal storage, not just diurnal. Seasonal storage for when renewables are not available. And what we can do is basically, when there is overgeneration of renewables, for example, in this case, solar during the middle of the day, maybe wind in a seasonal basis, store that electricity in the form of green hydrogen and use that to meet the demand when basically renewables are not available. And so in addition to using kind of these renewable electricity generators at their maximum capacity, we would also like to use low carbon technologies at their maximum efficiencies. And that's where I'm coming to, and that's where my research in EPRI is focused on. That is maximizing the use of hydrogen production from renewables, but also investigating how we can lower the costs using the approach of maximizing hydrogen production. So this is the results of the work that I did in my PhD, which I'm able to build upon at EPRI, and that is look at different operational profiles. So I had an example over here of forecasted curtailed wind profile in Ireland for 2030. So we use this as a base case, and we have we generated three different operational modes. There is basically the total energy used throughout.
So there's 2 minutes.
Sure. Yeah, I'll be quick. Yeah. So we have different operational profiles, which looks at KSP is a constant operation throughout the year. We have daily profiles throughout the year. And basically what I concluded is that in a high temperature electrolyzer, where we have high thermal response, the maximum hydrogen production is in KSP when we have a constant operational profile. Where in low temperature electrolyzer, there was about maximum of 7.7% variation, basically minimal variation between the 4 cases. That is to say, it didn't make a very big difference as to which operational mode we use. And this is the topic in which I want to build upon at EPRI, and we're working towards understanding how we can maximize green hydrogen production while keeping the costs low. I'll finish my talk with that, saying that, so basically just a link to engage with EPRI, engage with our research, not just the research at the electrolytic process team, but LCRI wide research. So we have something called the Technical Collaborative Network, which where basically a lot of universities, industries are able to engage with our research, and you don't have to be a member or anything to be a part of it. And we have an upcoming event on the 25th of May from 11 a.m. to 1 p.m. ET. That would be 4 p.m. to 6 p.m. GM British Standard Time, so it's not that late, luckily. So I suppose I could just skip over the slide and just say that apart from just contacting me, which I would be very, very happy to get in touch with anyone, you could also contact our program leadership and PSC leads. I've just put their contact information just so we have that, and that's about it. Thank you so much. I hope you enjoyed it.
Thank you.